water, as Amanda was talking about, as sort of this universal solvent that can dissolve all kinds of stuff, is that in ocean water, there's all kinds of stuff dissolved. The dominant ions are sodium and chloride, but there's all of this other stuff too. There's potassium and magnesium and calcium and all sorts of ions from different elements that are dissolved into the water as well. And so for marine algae and things like that that live in the ocean, they don't have to root into soil to extract all of those elements to build structures that they need. They literally can just get it from the ocean water that's floating around. So it's just kind of neat to think about, ocean water, it's salty, but when you're tasting it, you're not really just tasting sodium and chloride, you're tasting all sorts of different ions that are dissolved in there as well. So we've had a really good introduction to water and the unique properties of water. And just one last little thing about water that we're going to talk about before we move on is this idea of the pH scale. And I know that you have all heard of the pH scale, and that is a really broad tip. The pH scale is just a measure, it's a standardized measure of acidity. And what I want to talk about is what acidity is. So you've heard of pH, undoubtedly, at some point in your life. And you've heard of acidity, undoubtedly. But when we talk about the pH scale, what are we actually measuring? Well, the pH scale goes from 0 up to 14, this standard scale. And what it's measuring, the number is just a measure of the relative concentration of these H+ ions that are floating around. So one of the weird things about water is that, and the truth is a little more complex than I'm going to tell you right now. And if you want to learn more about it, you can take a chemistry class and learn more details about what water does exactly in this case. But in the simple form, water, which exists as H2O, which we know is oxygen with 2 hydrogens covalently bonded to it. Think how much you've already learned today. It's so exciting. What happens spontaneously in solution is that this water will actually dissociate, release an H+ ion and an OH- ion. And then there's some other stuff that happens, but in addition, those can just come back together and reform a water molecule. So they fall off and come back on, fall off and come back on. And even in pure water, totally pure water, unadulterated with anything, there's a concentration of these H+ that are just floating around. Just standard concentration. And so with the pH scale, 7 is set as the measure of the concentration of H+ in pure water. Anything that deviates it towards more H+ brings it lower on the pH scale. Anything that deviates it towards less H+ brings it to a higher number on the pH scale. So on the scale, this is more acid, which equals more H+. Over here is less acid, or we call it more basic, which means fewer H+. So if I gave you a solution and said, hey, here, taste this. First of all, you shouldn't taste it. But if I gave it to you, would you be able to tell if it was skewed towards the lower numbers on the pH scale by tasting it?
Maybe. Is it acidy? Like citrus?
Sure. So examples would be things like citrus, right? You taste it and you're like, this tastes...
citrusy. I just say acidic. That's what.
What's another word we use for that? Tangy and sour, right? So when you taste something that's sour, what you're tasting is a measure of the acidity. The more sour it is, the more potently acidic it tastes to you. But the crazy thing, Don't taste bad or gas. But I just want you to, this is one of those things that kind of like, it's kind of weird to think about. So what is acidity measuring again? What's the scale? What are we really measuring? Concentration of H pluses. And what are H pluses?
Positively charged.
Positively charged what? Hydrogen ions. So thinking back to hydrogen, all right, what's that number? Atomic number, which equals protons and electrons. This is atomic mass, which is neutrons and protons. So how many neutrons does a hydrogen atom have?
How many neutrons?
How many neutrons
One.
does a hydrogen atom have?
Okay.
Say it louder. None, right? So look, you've got one proton, and the atomic mass is also 1. That means that there are no neutrons. So now, what are you tasting when you taste acidity then? Protons. That should be like, think about it, like you can taste, you think about, this abstract idea like protons and neutrons, like we have no idea what they really are, but you really actually, on your tongue, have the ability to detect the relative concentration of protons in solution. What's going on actually at the protein level in your tongue is obviously probably a little more complicated, but think about how cool that is, that you can measure with your tongue the relative concentration of a subatomic particle. If you don't think that's cool, I don't know. There's no hope. So, okay, we're gonna cut that. So the other thing I want to do is I want to extend what Amanda talked about with abbreviations that we use. So instead of having to draw, the oxygen and all of the electrons and all the protons and neutrons and the shared electrons with its neighboring hydrogens, we abbreviate it as this or even H2O. And when you watch the video, it talked about the most important elements for biological systems. And do you remember the acronym they had? SCHNOPS. So one of the letters in there is a C, and it stands for carbon. And it turns out that carbon, partly, because of its incredible architectural flexibility, like this guy can form 4 bonds in these cool different directions, whereas oxygen has the ability just to form 2. Carbon is the scaffolding atom for all biological molecules. So any biological molecule you look at will have carbon as its core. It might be 1 carbon, it might be hundreds and hundreds of millions of carbons connected together. And it's so abundant that we don't even write C's out when we draw structures of molecules. So what we do instead is let's say I have this molecule here, C connected to a C, connected to a C, connected to a C, connected to a C. All right, everybody good so far? Now, this carbon is sharing a pair of electrons with this, so that means 2 of its outer shell are accounted for. So I'm going to add some other bonds to make sure it has its full complement of 8 electrons. And I'll move on to my next carbon, and the next carbon, and the next carbon, and I'm getting kind of sloppy here. And our final carbon. Now, that was kind of a painful process, wasn't it? So what we do to abbreviate when we draw chemical structures, and this is something you just have to get used to seeing, like seeing through the lines to what's going on with the atoms, is we abbreviate this molecule like this. Carbon carbon number 2, carbon number 3, carbon number 4, carbon number 5. These two things are equivalent to each other. Carbon, 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 carbon. If you don't see anything else attached to it, it just means everywhere you can attach a hydrogen, there is a hydrogen attached. So if you zoom in on this spot right here, it's just talking about that carbon right there. Okay. So what do you think about, let's draw this out. What do you think that is?
Carbon base with.
So remember, each time there's a starting line or a junction of lines, it's a carbon connected to a carbon. Okay? So if we zoom in on this, what's this going to be? A carbon connected to a carbon. What else is connected to this carbon? Hydrogen. All right, this carbon, well, it has 4 bonds. One goes to the first carbon. There's going to be 2 H's on it. And then one other line is going to an O with its own H. Yeah?
I understand the carbon part. How did we know that there was hydrogen? I mean, because it had already been premised? Because hydrogen is just as common as carbon? And that's what we're always looking at? I'm not
The
sure.
only way, so this is just a shorthand abbreviation. And so the standard is, if you draw lines with nothing else, it's carbon with hydrogens on it.
Okay,
So there's nothing inherent about lines that means anything. It's just a shorthand abbreviation for.
So hydrogen is also equally as common as carbon, and that's why they've also eliminated the
Sure.
hydrogen now. Okay.
Yeah. Yeah. So when you sketch it out, you don't bother with the carbons or the hydrogens. You only focus on anything else other than those. Everything else, the other groups are what are really going to matter.